In the silent blackness of space, something happened that should have been impossible. A star exploded, violently, brilliantly, just 642 light-years from Earth. Its name, Betelgeuse. For centuries it pulsed faintly in Orion's shoulder, a red glow in our night sky. Then, without warning, it collapsed. NASA's James Webb Space Telescope captured every moment: plasma jets, shock waves, magnetic storms, all recorded in real time in crystal-clear infrared detail. This wasn't an artist's rendering. This was raw cosmic truth, a front-row seat to a star's death, one we were never meant to witness. Had Webb not been watching, had the cameras not been rolling, no one would have believed this story. Nothing like it had ever been seen before. Not this close, not this clearly, and not with such profound implications. This was more than science. It was a once-in-history revelation. For years, astronomers had their eyes on Betelgeuse, Orion's famed red supergiant, flickering in ways it shouldn't. Its light, once a beacon of constancy, wavered, dipping, then surging unexpectedly. Observatories logged these anomalies with concern, whispering that the star might be shifting. As Dr. Elena Sotto put it, "It's as though the star was taking a hesitant breath, holding in secrets we weren't ready to face." Her poetic phrasing captured a mounting unease. Could a collapse be near? Under Webb's sensitive guidance, the star's surface revealed increasingly chaotic behavior. Gigantic convective cells, planet-sized masses of hot gas, rose and fell, bulging and fading erratically. Each bubble's appearance felt like the surface was bruising under immense pressure. Temperature measurements fluctuated by tens of degrees in just days, an anomaly unheard of in evolved stars. We knew something was brewing, physicist Dr. Priya Malik noted, but we weren't prepared for the scale of this unrest. Then came the sudden drama, a precipitous dip in brightness, the kind only a collapsing shell could cause. In mere hours, Betelgeuse dimmed more than most red supergiants do over months. Webb's NIRCam flagged it immediately. Simultaneously, neutrino observatories registered a spike, proof that the core's interior was roaring. It wasn't just a fading star, it was the prelude to something far more violent. "When those neutrino counts spiked," said Dr. Malik, "we grasped this wasn't a hiccup but a breaking point. Humanity realized Betelgeuse wasn't resting, it was dying. Its outer layers were unstable, thinning, ready to give way. Gravity began to reorganize mass within, preparing for collapse. But even then, no one fully grasped how quickly or dramatically it would unfold. The hints had been subtle, almost literary, like a star holding its breath before a scream. The calm shattered in an instant. What followed could only be described as cosmic pyrotechnics. Webb captured the impossible. When the supernova began in earnest, its instruments pivoted instantly, urging a cosmic camera into motion. Within seconds, high-resolution infrared frames revealed gas jets ripping through the star's atmosphere. Plasma textures shimmered. Shock waves rippled outward. It was raw, unfiltered cosmic violence played in close-up. MIRI's spectrometer provided the real wonder. By dissecting the light into its wavelengths, it revealed temperature maps across the expanding layers. Plumes that glowed white-hot contrasted with cooler pockets tinted red. "We watched convection patterns fracture and shift in real time," Dr. Malik explained. "There was no waiting, no post-processing, just a real-time ballet of destruction and beauty. Bright filaments appeared. Magnetic loops formed and snapped, invoking imagery of solar prominences, but on a vastly larger scale. Gas jets pierced surrounding space, some shooting outward at relativistic speeds. Webb tracked each plume's evolution minute by minute. Layers of heavy elements surfaced: iron, silicon, nickel, the unmistakable signatures of a nuclear furnace. It was more than a telescopic record. It was the first real-time infrared portrait of a nearby red supergiant's death. The detail shattered expectations. Every shockwave, eddy, and plasma burst became visible. "This changes how we visualize supernovae forever," astrophysicist Sasha Long reflected. Previously, such events were painted by inference. Now Webb offered real images of real phenomena and matched them with quantitative data. From these infrared flames and spectral maps, the story deepened. As the explosion progressed, gravity fought back. What should have been a straightforward outward surge, instead mixed with inward falls. Webb's instruments spotted certain gas, clumps failing to escape. Some chunks of stellar mass reversed, collapsing back toward the core. This asymmetry spawned unexpected shockwaves that rebounded, fracturing the blast front. Earth-based gravitational wave detectors reported irregular tremors, not the smooth chirp of a symmetrical collapse, but jagged signals hinting at a tumultuous core. "We saw gravity flexing like a broken wave," Dr. Malik said. Betelgeuse's heart was oscillating, rebounding, and unevenly collapsing. Magnetic fields added another layer of complexity. As charged gas moved chaotically, fields twisted and braided. Observations picked up plasma voids, bubbles where fields repelled matter, and narrow jets aligned with magnetic poles. Some plasma pockets were accelerated to significant fractions of light speed. These weren't textbook supernova features. They signaled something deeper. The collapsing layers formed turbulent fallback dynamics. Dense chunks fell inward, heating and compressing, only to be thrown back by core pressure. Each layer, core, mantle, atmosphere, transformed differently over time. Webb's final frames of the sequence tracked this dance, filming each phase transition as if slicing through time. Scientists gathered around screens. Statements like, "I can't believe we're seeing glitch-like gravity and plasma jets in." The same event echoed in control rooms. This wasn't just messy, it was a cosmic lesson. Gravitational collapse wasn't a smooth fade to black, but a violent tug-of-war where matter, magnetism, and gravity wrestled before life's ingredients were cast across the cosmos. In the hours following the collapse, something remarkable happened. Webb's MIRI instrument began detecting radioactive elements, technetium, yttrium, and iron-60, blasting outward in the shock waves. These were freshly formed in the crucible of the explosion. It was like watching the periodic table being written in fire, said astrophysicist Dr. Kamal Rashi. The arrangement stunned researchers. These isotopes weren't randomly scattered. They followed thermal gradients, flowing in layers like cosmic fingerprints. The ejected technetium and aluminum-26 matched signatures found in ancient meteorites from Earth's early solar system. "It's like we're looking at our own past," Rashi explained. "This is the raw material that seeded planets like ours, now forming right in front of us." Even more surprising was the presence of phosphorus, an element vital to DNA and biological molecules. Webb detected it forming earlier in the explosion than expected. "This shifts how we think about life's building blocks," said astrochemist Dr. Louisa Mora. Previously, phosphorus was thought to emerge in late supernova stages or in slower secondary processes. Now, it was forming near the moment of collapse. The death of Betelgeuse wasn't just destructive, it was a creation engine, spitting out the seeds of planets, atmospheres, and biology. Webb gave us a front-row seat to the exact process that made our world possible. For the first time, scientists saw, not inferred, how stellar death lays down the chemistry for life. What happened next added a new chapter. The shock waves didn't just radiate into silence, they began shaping their surroundings. Webb captured the ejected gas flowing into structured shapes. The cloud formed a bipolar outflow, jets in two opposing directions, carrying core materials and carving space. Denser pockets formed inside nearby molecular clouds, already beginning to collapse. These are how stars begin. Gravity pulls gas together, igniting new fusion. Betelgeuse's shockwave wasn't just explosive, it was fertile. Observations from Alma and Hubble confirmed protostellar activity. "We're watching a nursery form," said Dr. Moira, "from a grave to a cradle all in one shot." Webb also spotted something eerie, shockwave rings like ripples in water, expanding. Shells that weren't smooth. They contained ridges, evidence of earlier eruptions long before the final collapse. Some dated back 10,000 years. "It's like a time-lapse of the star's whole end-of-life cycle," said Dr. Soto. These rings weren't passive. They reshaped the interstellar medium, compressing it, ionizing it, altering its chemistry. Betelgeuse's death didn't end its influence. It restructured its entire region. And Webb let us see that change unfold, not over centuries, but in weeks. Even with debris expanding and newborn stars igniting, Betelgeuse wasn't finished. Strange signals began to emerge. Radio bursts, pulsing flickers, and gravity waves unlike anything seen before. Weeks after the collapse, low-frequency bursts reached Earth. They pulsed rhythmically, then spiked with strange harmonics, not alien, but not ordinary either. These bursts didn't match any known red supergiant behavior, said radio astronomer Dr. Lara Green. The signals possibly marked the birth of a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's. The bursts were paired with rhythmic infrared flickers, symmetrical light pulses. It was like the core was spinning, sending a light beacon into space, Green said.